Section 7.4, the sampling distribution of a sample mean. In the last section, we talked about sampling distributions of a sample proportion, which is the kind of sampling distribution we use when we're dealing with categorical data. When we have quantitative data instead, rather than use a proportion, we'll be using a sample mean, denoted by the variable x bar, to estimate the mean of the population, mu. Just like our sample statistics from proportions, x bar is going to vary from sample to sample as we're using it to estimate the true population mean, which is constant. To understand how much this sample statistic varies from the population parameter, we're going to talk about the sampling distribution of a mean. Just like we did when talking about sampling distributions for proportions, let's start by taking a sample of pennies and recording the year that these pennies were minted. In this example, we're going to take a sample of 5 pennies, and we're going to do that 50 times. When we take our sample of 5 pennies, we find the average year that they were minted. That's our x bar. It's the sample mean. And every time we take a different sample of 5 pennies, we get a different x bar. Just like proportions, we're going to start to see these pile up around some value. Now, this is still a bit skewed to the left, and that's because this sample size is small. We'll talk about that in a bit. All right, but the larger that sample size is, the more approximately normal that it would be. So just like proportions, the mean we get from our sample x bar can be used as a stand-in for the mean of the whole population. X bar is an unbiased estimator, meaning that when we take a mean, or we take a sample from the overall population, we're most likely to get something that's close to the actual mean of that entire population. As for the standard deviation, there's a new equation. We don't have a P and a Q anymore, so we can't use this equation that we did in the last section. And instead, we're going to use this one, sigma over radical n. This standard deviation behaves exactly as it did for proportions, including the way there's less variation for larger samples, meaning that as n increases, the standard deviation is going to get smaller, and it's going to get smaller in the same way that it did with proportions. So let's say instead of taking a sample size of n, we take a sample size of 4n, right? That's inside that square root there. Okay, we could separate it out, and we can see that by increasing the sample size by a factor of 4, it decreases that standard deviation by the square root of 4, or 2. As for the conditions that we need to implement a sampling distribution, the first is the same. We need to have independent observations, which is normally not the case because when we select something, we can't select it again. But just like with proportions, if our sample is less than 10% of the population size, we can consider those differences negligible and just pretend that they're independent. As for the second condition, just know that when we're dealing with small samples, our sampling distribution is going to retain the shape of the overall population. So if our population distribution is skewed to the left, the sampling distribution will be skewed to the left also. That said, if our population distribution is normal, any size sample is okay to make a sampling distribution that's approximately normal. If it's not normal, if it's skewed, or if we don't know the shape of the population distribution, we want to have a sample size that's greater than 30. If that's the case, we'll have something that's approximately normal. For example, the number of movies viewed in the last year by students at a large high school has a mean of 19.3 movies and a standard deviation of 15.8 movies. Let's say we select a simple random sample of 100 students and calculate the mean number of movies viewed. So to start, our sample is less than 10% of the population. We're going to assume that there's over 1,000 students at the school, which is probably true. And our sample size is greater than 30, so it doesn't matter if this distribution is skewed, normal, etc. Our sampling distribution will be approximately normal as long as that sample size is greater than or equal to 30. So we're going to start by calculating the mean and standard deviation. Mean is just what we get in our sample, 19.3. Standard deviation, we're using this equation, sigma over radical n, because as our sample size increases, this standard deviation changes and it gets smaller. So we're going to take that 15.8 and we're going to divide it by the square root of the sample size, and we get a standard deviation of 1.58 movies. Standard deviation is the average distance from the mean. So in simple random samples of size n equals 100, the sample mean number of movies typically varies from the true mean by about 1.58 movies. At the P-Nutty Peanut Company, dry roasted Shell's peanuts are placed in jars labeled 16 ounces by a machine. The distribution of weight in the jars is approximately normal, with a mean of 16.1 ounces and a standard deviation of 0.15 ounces. X bar is going to represent the mean weight of 10 randomly selected jars. Let's describe the shape, center, and variability of the sampling distribution. So the shape is going to be approximately normal because the overall population is approximately normal. The center will be the average of our sample. And the variability, this standard deviation is going to change based on the size of that sample. So we'll take that 0.15, we'll divide it by radical n, radical 10, and we get a new standard deviation of 0.047. In part B, we're going to use those values to find the probability that the mean weight of 10 randomly selected jars is less than the advertised weight of 16 ounces. So that mean is going to go right in the center, the mean of 16.1. When we found the standard deviation was 0.047. So this is our distribution, and we want to find, is it unusual, or what's the probability of getting a peanut jar that has less than 16 ounces of peanuts in it. So we find that z-score, we look it up in the table, and we get our answer of 0.0166. When we're working with sampling distributions, remember that individual values vary more than averages. So if we're just talking about one jar of peanuts from this distribution, it's much easier to get a single jar that's less than 16 ounces compared to a sampling distribution where we're selecting 10 jars. As we average the weights of these 10 jars, we're going to get things more and more consistent with that mean, where it's harder to get an average of 10 jars less than that 16 compared to a single jar less than 16 ounces.